Hello guys, as I am discussing Queen theory series, so in this previously I discussed what is the concept of model number 1. Now on the basis of that I am going to discuss what are the some examples of model number 1. So here the first one I am going to discuss is type 1 problem in this model number 1. So the problem is statement is like that a self-service store employees hire one cashier at its counter and now 9 customers arrive on an average every 5 minutes. Well, the cashier can serve only 10 customers in 5 minutes. So assuming Poisson distribution for arrival rate and exponential distribution for service time. So we have to apply this and find out some like what is the average length of queue, what is the time required to serve customers in the queue, like that ls, lq, ws and wq. So first thing is there, uh, we have to find out lambda and mu. Lambda is what? Arrival rate, and mu is what? Service rate. So for arrival rate, so as arrival is saying that there is 9 customer arriving on a average of 5 every 5 minutes, so it will be 9 by 5. So we can write it in mathematical form 1.5, but it is nothing like 1.8 customer per minute. It will be 1 or 2 or like that. So to simplify our problem, I have written that 1.8 customer per minute. So mu will is the service rate. So service rate is saying that 9 customer a cashier can serve in 5 minutes. So 10 by 5. So here I will get 2. So customer 2 server will serve in per minute. Now lambda and mu are there. So first we have to find out what is the average number of customer in the system, that is ls. So for ls, just write that formula. Ls is equal to lambda upon mu minus lambda. So lambda is equal to ls is equal to lambda upon mu minus lambda. It will, so put the respective value of lambda and mu, we will get 1.8 divided by 2 minus 1.8, we will get 9 customer. Accordingly, if we proceed for average number of customer in the queue or average queue length, so that the question is saying that find out the lq value. Lq is nothing but lq is equal to ls minus lambda by mu, or we can also write this in the lambda and mu form, that is lq is equal to lambda upon mu multiplication with lambda upon mu minus lambda. So it will be equal to 1.8 divided by 2 multiplication with 1.8, 2 minus 1.8. So it gives us 8.1 customers. Okay, but it will be equal to only 8 customers, not 8.1 customer. Okay, so mathematically it is written, but it is equal to 8 or 9. Okay, so what is average time a customer spend in the system, that is ws. Ws is equal to, as it is saying that average time, so time for w and spent in the system for s. So ws is equal to ls divided by lambda. So ls divided by lambda will give us we use simple formula for ls. ws is equal to ls upon lambda, or ws is equal to 1 upon mu minus lambda. It will equal to 1 upon 2 minus 1.8, it give us 5 minutes. Okay, so we have calculated ls, lq and ws. Now the time for wq. Wq is nothing but average time a customer wait before being served, that is wq. That is average time required a customer to be served, in that he will be in queue only. So wq is equal to lambda upon mu minus mu multiplication with mu minus lambda. So put the respective value of lambda and mu, we will get 4.5 minutes. Okay, so this is the simple problem of model number 1. I have discussed with only simple terminologies here, ls, lq, ws and wq, such things. But now the time for type 2 problem in model number 1 only. Okay, so here problem statement is saying that a person repairing radio and find that the time spent radio set has exponential distribution with mean 20 minutes if the radio are prepared in the order in which they come. So in and their arrival in approximately Poisson with an average rate of 15 for 8 hours per day. Okay, so what we have to find out, what is the repairman's expected ideal daytime, and how many jobs are ahead of average set. We have also to find this one, how many jobs are here on ahead. Okay, so for that, just first we have to find out what is the value of lambda and mu here. So lambda is nothing but arrival rate. So arrival rate means 15 uh, are request for 8 hours per day. Okay, so 15 is divided by 8 multiplication with 60 to convert in minute, so it will give you 1.32 units per minute. Okay, so service rate, it give mu is equal to 1 by 20, it gives us unit in minutes. Okay, now what average number of jobs in the system, that is ls, we have to find out. For ls is nothing but lambda upon mu minus lambda. Put the respective value of lambda and mu, we will get here on solving this mathematical expression, we will get 5 by 3 jobs. Okay, and now we have to find out the number of hours for which the repairman by busy in 8 hours per day. Okay, so for this we have to calculate multiply 8, as it is given that 8 hours per day multiply with utilization factor, that is mu, so it will give us 5 hours. Okay, so time for which repairman remains ideal in 8 hours per day, we have also to find out here this one. So as the number of hours for which repairman is busy is 5 only, right? So it means that in 8 hours only 5 hours he is working, so remaining ideal time will be 8 minus 5, so simply it will be 3 hours only. So this is the type 2 model for uh, model 1 in Quine theory, and now the time for type 3 questions in model 1 only. So for that I have taken this example. So type 3 problem is states that a branch of bank has only one typist. Since the typing work varies in the length, the typing rate is randomly distributed, approximately a Poisson distribution. So it is clear that our distribution is following Poisson distribution with mean service rate of 8 letters per hour. The letter arriving at a rate of 5 per hour during the entire 8 hours work day. If the type writer is valued rupees 1.50 per hour, we have to determine some things on the basis of this record. So simply here first we have to find out that what is the value of lambda and mu here. So simply here equipment utilization factor is mu rho, so rho will be lambda by mu. So what is arrival rate? Arrival rate is given as 5 letter per hour are coming, so it will be 5, and the service rate, that is mu is equal to 8 letter per hour, so utilization factor will be lambda by mu, it will give 0.625. then the present time and arriving letter has to wait. So how much time a letter has to wait, we have to find out this percentage time arriving letter has to wait. For this we have to multiply it with this one utilization factor, that is this is the total utilization of a server, so it means percentage time arriving letter has to wait will be multiplied with 100, it will give 62.525 62.5 percentage, this one the percentage time and arriving letter has to wait. Then the third thing is simply average system time, that is WS. So what is WS? Simple use formula for model 1. WS is nothing but 1 by mu minus lambda. Put the value of lambda and mu, that is lambda is 5 and mu is 8, so it will give 1 by 3 hours. So in converting in minutes it will only 20 minutes only. Now we have to find that average cost due to waiting on the part of typewriter per day. Okay, so what is will be the average cost? Simply here average cost due to waiting on part of typewriters per day, so it will be busy time. Busy time is nothing but we have to multiply that our this is 5 by 8 is nothing but our utilization factor, and type vector work for a day will be 8. So multiply 8 with 5 by 8, it will give only 5 hours. So remaining time will be 8 minus 5, so it will be 3 hours. Now as the question is saying that rupees 1.5 per hours is given to typewriter, so total cost he will earn, remaining ideal time he will gain that 3 hours is there, so multiply 1.5, so it will give 4.0 rupees. Okay, so this how we are able to see that what is the type 3 problem in this one Quine theory. So this how I discussed that this one is type 3 problem and model number 1, and this one is type 2 problem in model number 1, and this is the type 1 problem in model number 1. So there are basically 3 types of problem in model number 1 in Quine theory. So go through it and find out some useful things, and thank you very much for watching these videos.